Hello everyone, April the 10th. Alright. Removing stars from a string. Oh, I've done this before. You're given a string which contains stars. In one operation, you can choose a star in S, remove the closest non-star characters to its left, as well as remove the star itself. Return the string after all stars have been removed. The input will be generated such that the operation is always possible. It can be shown that the resulting string will always be unique. So in the first one, we'll remove the star, choose a star, remove the closest non-star character, okay? So LECOE, LECOE. Oh, I think today we're testing stack, right? Yep, we're testing stack. Okay, this one is stack. Okay, let's do stack. For letter in S, if, well, it does say it's always possible, right? That's what it says, so maybe we don't have to check. I mean, it's better to check. Yeah, I'll check. If stack, no, if stack, if letter is equal to this, right, and stack, then stack.pop. If letter is not equal to, so what happens? Yeah, we just remove that, right? You know what? It says it's always possible, so we probably don't have to consider that situation. That'll be easier then. Else stack.append letter, and then we'll return dot join stack. I think this shall be enough. Yep. 2022, November the 7th. That was the last time I did this. I can actually check. Well, probably can check the solution. This is the last time. Yeah, it's the same thing. Stack. 2 pointers? Wait, hold a second. Yeah, stack we know. String. Isn't that the same thing? 2 pointers. Point to the position where the most recent non-star character is to be inserted. It will also help in removing the characters. We create an array. Ah, a slow and a actually, I wanna try this. A slow and a fast, right? Let's try the 2 pointers. 2390. Use stack. Okay, that's solution 1. Let's try solution 2. 2 pointers. 2 pointers. From the official solution. Okay, we'll have I, J go to 0. One of them will keep going forward. Right, for J, in range, line S. Ooh. list equals list s. Okay, if list I is equal to star, right? Wait, hold on. So we go, right? Go. Okay, the first thing. No, we should always fitting, right? And filling this, then this is a move, and let's just go forward and we're filling. So I think it shall be here. List equals, doesn't matter, multiplied by, I can just do this. Oh, in this case, I don't even need I. I mean, isn't that just look like a stack? Well, no, because there's no pop. Hold on, so we'll push. And if it's, we will not push. You know what? I don't think it's necessary. Yeah, I know how it works, but it doesn't make any sense. I don't like it. Stack is the way to go. All right, back here, I can check the other people's solutions. Okay, what is it about? Or. Okay. Power of 2. Yes, it is power of 2. Lordy, you gotta be kidding me. Okay, if 1 not in A, return 1. If 2 not in A, return 2. Yeah, because we cannot do. Yeah, it is power of 2. Find the minimum power of 2. Oh. Shoot. It does make sense. We already find it, right? We know if it's consecutive, then the answer is this. Like, this is the one that's not, actually this will be better. This is the one that's not in it, which is essentially power of 2. Exactly. So if 1 not in, if 2 not in, right? If 4 not in, if 8 not in. Ah, yeah, they are all power of 2s. Oh my god. Good. Yep, power of 2. From Lee 255. Yeah, I didn't notice, right? I didn't notice. But the answer, right? The answer to the problem is always going to be power of 2. We have already seen it. We have already done it, actually. Right? When we say the smallest integer, right, that cannot be formed by a series of consecutive integers is the largest such is the largest is to fill, right? To fill binary version, right? The binary, fill all the binary positions of the largest consecutive integer with 1 and then plus 1. That would give us a power of 2. Hence, the problem is akin to finding the first power of 2 that does not exist in nums. So we say nums set equals set nums, right? Then we say for, and we can do 10 to the 5th. 10 to the 5th. 10 to the 5th power what? 10 to the 5th. Log this bit divided by log 2. Wait, hold on. Is it 16? No, 10 to the 9th. 10 to the 9th. I think that's 30. We can do 30. Right? We can do 30. So we say for I in range to 30. If 2, 1 left shift I is not in num set, then I return 1 left shift I. Yep. What are you going to return at the end? What if everything is in it? Well, I do 30, so it's not possible. Because I do 29. I might as well just do 31, because 2 to the 30, 2 to 29, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it's already, yeah, 29 is fine. I think 29 is fine. I already covered the largest. Let's try this. Huh. That's interesting. So I need to be larger. 31. Oh yeah, the largest is 10 to the 9th, right? That's the largest, which is 10 to the 9th is 2 to the 29th power, right? So we have 29 positions, every position is 1, and then it can be larger than this. So it has to be 30. Okay, so it has to be 30. So it has to be 31. Yeah, it makes sense. It has to be 31. It's not 30. It has to be 31. 31n. Okay. That's that. All right, we hit in this one. Let's see. Handling what? Some queries after update. Ay. 2 0 indexed, nums1, nums2, and a 2D array queries. There are 3 types of queries. For a query of type 1, L and R flip the value from 0 to 1 and from 1 to 0 in nums1 from index L to index R. Both are 0 indexed. For the query type 2, P0 for every index 0 to n. What's n? What the hell is n? Is n the length? I guess n is the length. It didn't say what is n. I guess it's length. We'll do nums2i equals nums2i plus nums1i times p. For query 3, find the sum of elements in nums2. Return an array containing all the answers to the third type queries. Holy crap. Okay, so query first one is a toggle. Okay, the first one is a toggle. 1 to 0, 0 to 1. And nums1's only 0 and 1. And nums2 can be large values. So we do query 1. After the first query, query 1 becomes 1, 1, 1. Wait. Query 1, flip the values. So toggle it from L to R. So now L and R both are 1, so we toggle 1, so that's a 1, 1, 1. Okay, makes sense. Query 2 will get everybody on 2 equals this plus query 1 is everything here multiplied by p. Now p is 1, so nums2 become 1. And query 3, we just sum it up, so that will become 3. You know what I'm thinking? I'm thinking we can use Numpy for this. That's what I'm thinking. I'm thinking we can use Numpy for this. I'm gonna use Numpy for this. Like, pretend, right? Pretend we are during the contest, and then we always try to. It might not work. Right? Numpy is fast, but who knows, right? It might not work, but hey, it's fun. It's fun to try it. So if we want to do a Numpy, let's say import. Yeah, I don't care. Equals numpy.array. Nums2 equals numpy.array. Nums2. Right, res equals this. And a for query. Let's call it QAB. How about that? QAB. QAB in queries. If Q is equal to 1, then nums1. Oof. Actually, I'm not quite sure. I'm just going to try this. Oh, do I even have Numpy globally? I do. Huh. No, it's not globally. It's locally. Okay. What do you want? Let's say a equals numpy.array. Right. 0, 1, 0, 1, 1, 0, 1, 1, 0. It doesn't really matter. I just want to try. And let's say a. Let's say 0, 1, 2, 1, 2, 3, 4, 1, 2, 5. Okay. Yep. Let's say this equals. Not sure if this is gonna work. No. Okay, that's not how it's done. How do we? Oh Lord. I already changed the a value. Go back to a. How do we toggle? Exclusive or. 1 toggle to 0. So exclusive or with 1. Yeah, exclusive or with 1. Can we exclusive for, oh my god. Like this? No. No, exclusive or with 1. Dear Lord, man. It's a equals exclusive for numpy dot ones 4, right? We have 4. Interesting. Oh, D type equals, can I do this? Okay, so can I do this? D type equals int? Yes. Okay, so that seems to be working. So if that's the case, then we say nums1 from L to A to B, right? A to B plus 1, exclusive or equal to numpy dot ones B minus A. D type equals int. That work? Yeah, so if Q, if Q is equal to 2, then nums2 equals nums1 times, no, nums2 equals plus equal to nums1, right, times P, which is A, right? P is going to be A. Else rest dot append numpy dot sum nums2, right? Sum of elements, and we'll return rest. Now this will work, I think, but I don't know. How fast do you think numpy can get? Can we pass it? I think that if I were to design this problem, I would definitely make sure that numpy will not pass. That's just me. Like, otherwise, what's the point, right? The point of the problem is to figure out smart ways to do this. And when you use a numpy, that's just being lazy. But if I don't try it, I'll regret. So always try it first. My lord. Non-broadcastable output. Huh. What? Which one? Ah, 1 1. Oh, I need the plus 1, right? Look at the overhead. Numpy's overhead. Well, give it a shot. Like, why not? If it times out, then it times out. Then we think about the good way to do so. Oh, Jesus. See, this is not something good. Pray that in reality, this will not happen. Should have run the code first. Should have run the code first. This is like, you add what, 5 minutes, right, to your final result. Ooh, it's not gonna work. It's not going to work. Oh, it does. I was just going to say it's not gonna work. All right, Numpy. Numpy cheating solution works. Surprise, surprise. All right, so nothing to say, right? It was terrible runtime, but hey, passing is a passing. All right, now we passed this. Now we can start thinking about how to do it smartly. Okay, so we know the mechanics, right? We know the mechanics. What do we need is every time is a 1, then we will so A is just going to be nums 1, right? Nums 1 is just going to be a bunch of 1 and zeros, right? It doesn't really matter, just 1 and zeros. And nums 2 is the actual thing, right? Whatever value it is. We don't really care about nums 2, the value. What we care about is how can we update, right? Basically, each update, we need to get the new value as fast as we can. Now, when we do a second query, we're only accumulating p, where we're adding p to whatever is 1 in nums 1. Okay? So let's say I will have, and before query 3, right, you can do query 1, and you can do query 1 again, you can do query 1. Every time you do query 1, you are updating plus and minuses, right? Okay. Maybe we can. We can what? Because the query 1 is toggle within a range, right? If 2 query 1s have an overlapping area, then those toggle will be meaningless. Okay. But what if there's a query 2? It doesn't matter, right? We keep track on the toggle. Can we keep track on the toggle? When we have a range, and then we have another range, and we have another range, or we keep track on where all the 1s are. Okay, we keep track on where all the 1s are. I don't know. Come on, let me think again. Because the 2, query 2 is very straightforward. Query 2 is just to add. Oh, if you think about it. Are all the values positive? Query I, P, yeah, P is positive, right? And we are always adding to nums 2, which means if we compute initially the sum of nums 2, and every time, and if you do query 1, it does not affect nums 2 at all, so it doesn't really matter. It affects nums 2 whenever we do query 2, and when we do query 2, we'll add all the position that's 1. We'll add the number. That doesn't really matter about the position. What matters is we want to know the number of 1s in nums 1, because every position that's nums 1, we need to multiply it by the p, right? Which is to say, if we can keep count the total number of 1s in nums 1, right? We have a count. Then every time we do query 2, this is that count multiplied by p. That's the additional value, right? We'll add to nums2. And then we're going to know the sum of nums2. So just the sum of nums2 plus p times the number of ones in nums1. That's what happens at query 2, right? So yeah, of course, it's going to be faster than the NumPy solution. So now we boil down to query 1, right? That's the only thing we need to worry about, is how do we keep count of the number of ones in nums1. Now we can always count the initial, right? We count the initial, and then every time there's a query, right? Query 1, then we have a range. And within the range, what we need to know is how many ones is inside this range, right? Or you can say how many zeros inside this range. And then we know when we do the update, then all the ones will turn to 0, the 0 will turn to 1, so the number of ones will change, right? And that would affect the total. So can we use something, let's say, oh god, binary index tree? Can we do that? I don't think so, because bit is you update one value. But here we have a whole range. You can't just update a whole range of values. Now I don't feel bit for this one. Well, maybe it is. But think. It's a range. And I definitely do not want to do segment tree. And I don't think it is segment tree, because we're saying in this range, right? In this range, let's say we have a prefix sum, right? That's the easiest version of this. We have a prefix sum, which gives us the count of the total number of ones in every range, right? Perfect. Now I give you a range, and I say I want to toggle it. Then what do you do? Then what do you do for this prefix sum? Then what it means is, within this range, let's say initially we have a certain number of ones. Now the number of ones will change, right? And when that changes, no, I don't want segment tree. Can you do segment tree? You change the value in this. I don't know. But keep in mind, we don't really care. We do care because it's a range. But do we really care? So we want a data structure, right? Once we say, I want to query a range, you can tell me how many ones is in there. And then if I toggle the ones, okay, that means an update. And I query it again, and it can tell me how many total ones there are. How many total ones? But we still need how do we do this faster? We have a range, and now we have some ones, some zeros, right? And I toggle it. And the number of ones in this range changes. And the total number of ones changes. That's all fine, right? That's all fine. But what is not fine is if the next time I want to query the same range, then I have a problem, right? Then I have a problem, because you have to assign the ones to the right position. I feel I've done something like this before, right? I feel like I've done this before. Can we segment tree this? But the segment tree this means you have to update every single one. Yeah, exactly. Like how do we know? Well, what's binary index tree? Binary index tree is I have a delta and I can update the value. Okay. So in this case, it's just a sum, right? It's just a sum. So I can just do good. And then the delta at each position could be, you know, if it's a 1, then we will just do a -1, right? If it's a 0, then we just do a +1. But the thing is, if you do that, every query, you will have to every query you will have to do the modification, right? But what if we think about it this way? Yeah, what if we think about it this way? Let's say we have a query 1, right? And then we have another query 1. We keep track of the query 1s, right? We keep track of the query 1s. And then we just say, okay, we'll have query 1, we'll have query 1, we'll have query 1. And each time we do a query 1, we merge the range, right? We merge the range. And whenever a query 3 appears, I just get it as a result. It doesn't really matter. And whenever query 2 happens, then we do one update over the entire range. That might actually be an interesting idea. So you have a range, right? So we say, oh, that's the toggle range. And then now we have another range and it overlaps, right? Whenever there's overlap, that range gets eliminated. Then we have separate ranges, and then a new range comes in, and we can merge, we also overlap, then they got cancelled. Okay. So what type of data structure are you thinking about if you want to do this range merge? Oh, I hate range merges. Dude. I don't like it. And we have to keep it sorted. We have to keep it sorted. It's okay. We can keep it sorted. So we keep it sorted, and a new range comes in, and oh my god. Oh my god. Yeah. Exactly. And then the logic is slightly different, right? If it overlaps. Oh man, I don't want to do it. I do not want to do it. If you're saying if there's something I don't like, segment tree, I don't like it because it's very complicated to write. And any algorithm to merge range, I don't like to write this. It's complicated, and especially the way I do. The way I do is I'll put it into a dictionary, and the key is the left edge, value is the right edge, right? And I'll sort the key, so I have left edge in order, and then a new thing comes in, and I'll binary search to find where it's supposed to be, right? And then I have to compare to now. Is there another way? I don't know, man. And the thing is, you have to merge like consecutively, right? Can we do it? Oh. I'm looking at a hint. What do you give me a hint? So I guess it is segment tree then. Ah, Lord. Okay. Yeah, I think our idea is correct. It's all about query 1, right? It's all about query 1. And now the question is, what the hell is lazy segment tree? The hell is lazy segment tree? Lazy propagation in segment tree. Segment tree and lazy propagation. Let's try this. Maybe we have to go segment tree first. You know what? We have to learn. We have to learn segment tree again. Like I don't know, every few months I have to go through this. Yeah, just very not intuitive. Anyway, so okay, segment tree is we have the sum. Yeah, and you have to do it as index, right? Which is okay. So, oh jeez. So you have the range, have the range sum, and then you have the range sum, and then that's the one. Yeah, it's slightly different the way compared to how I will construct it, but anyway. So that's the construction, right? You build the tree first, okay? So this will be the sum of these two, right? So you build the tree, and after you finish building the tree, now that's update. Wait, hold on. We have to have update. I don't get sum. Where is update value, right? Update. Let's look at Python. Update value. A recursive function to update the nodes which have the given index in their range. The following are parameters. But you're updating at a single position, right? You're updating at a single position, which means if you update at every single position, then you still cannot do it, right? Because you have a range, and this range is huge, 10 to the 5th. You can't just do one by one, one by one, one by one. But you kind of have to. I don't know. Guess some is easy. I'll have the tree, have the query start, query end, and segment start, segment end. What's SI? The hell is SI? Index of the current node. This is a node. What's ST? Pointer to the segment tree. So if query start is smaller or equal to segment start, and the query end is larger or equal to segment end, then we return the current sum at the segment. Really? That's how you do it? It's not how I do it. If your query range is larger than the current range, which is not supposed to be, right? Okay. So otherwise, if your segment range, your query start, is larger than query segment end, and segment start is larger than query end. So we have the segment start, segment end, right? And the query start is here, or query end is smaller than segment. Yep, that's a 0, right? That's a 0. Otherwise, we'll do get a middle. Otherwise, this means I think this is wrong. I think it should be segment start is smaller or equal to query start, and segment end is larger or equal to query end. I think this is wrong. I think it should be the other way around, right? Which means your query is in between. No, hold on. No. This is right. This is right. This is correct. If your query is like larger than the segment itself, just return that. Otherwise, because the initial segment is huge, right? So otherwise your query is within the segment. Then you split it into two, right? You split it into two, and you do the left half and the right half, right? The left half and the right half, and you plus them. Okay, so I got that. An update value. Oh, geez. Update value. Same thing. We have the segment, but is only I, right? And I, and that's the diff. And again, if I is smaller than segment start, larger than segment end, I return good, right? That means we cannot update. If the input index is in range, yeah, if it's in range, we have to update the diff. And if SE is not equal to SS, which means there's still, so we need to break into half, right? We break into half, and then we do the left half, and then we do the right half. That makes sense as well. right? And oh, that's just update value. That's okay. Get some. Construct. Yeah, but you update only one at a time. But I guess you can do one at a time. Okay, what's lazy propagation? I think I've read this before. Uh-huh. A single value update in an array may cause multiple updates. That's true. Yes. If array index to be updated is not in the current row range, then return else. Yeah, we know. We've seen this before. Don't have to do this again. What if there are multiple? Yes. What if there are updates on a range of array? Exactly. What if? Attend to all values at indices from 2 to 7 in an array. If it has to be called for every index, yes. So we can avoid this by writing a function update range that update nodes accordingly. What is this black magic? Update range. Okay, this is a segment start, segment end. Okay, segment start and, well, it's update end. If segment start is larger than update end, or segment or update start is larger than segment end, yes, then we return, so we don't update anything. Current node is the leaf node. Perfect. If not, recursion for children. So we have the left and the right. Segment start to mid. Use the result of children. But that's the diff is the same thing. Use the result of children calls to update this node. Huh. Interesting. Yeah, we have a range, and then once we hit the end, then we propagate back up. And every time we propagate back up, we just recalculate. We recalculate. Okay, this makes sense. We can postpone some updates. Then we need to update this node, and all descendants, yes. Only nodes. And postpone update to its children by storing this update information in separate nodes. Oh. 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 Alright, that's something for tomorrow. Yep, I have to use segment tree. Yeah, I think our analysis of the problem is correct, right? The issue is all with query 1, but now we need to use segment tree, and we have to do a range segment tree, and every one has to be different. So it's not this one, right? This is the easy case. It has to be this case. Oh well, I'll think about this tomorrow. That's okay. That's okay. Yeah, that's the learning process. This is where the learning comes from. All right, that will be it for today. I will see you guys tomorrow and go back to this problem. Adios.